In 1.5, we're going to be taking a look at solving inequalities. This is going to back us what we did in 1.3 and 1.4 when it came to solving equations and absolute value equations. Really, we have three objectives today. Solve inequalities with one operation. Those are pretty basic ones. We'll take a look at those first. Solve multi-step inequalities. That'll be where we spend most of our time, probably right around there. And then convert algebraic notation to set builder notation. We'll also be addressing, if we have time, we should, what we call interval notation. It's not really found in depth in your textbook, but we will be spending some time on it. Very important for that next level. It's just another way of writing this algebraic kind of notation that you're already familiar with. So let's first off solving inequalities with one operation. Now, there's a property here. You don't need to know this. It's almost a common sense property. You don't need to memorize this as much as the other properties, but the trichotomy property, which simply tri meaning three, simply means that numbers, when you compare them, fall into one of three categories. Of these three categories, either A is going to be greater than B. That could be true. I'll say A is 5 and B is 0. That would be true. Either A is less than B, so if A is 5, maybe B is 10, okay, and 5 would be less than 10. Or they could be equal to each other, 5 equals 5. And so those are the only three categories numbers fall into. It's a really pretty basic property, actually. It's pretty cool that a property like that we take for granted. Inequalities typically have solutions over an entire interval instead of in other words, what we're saying is this. With equations, we had a finite number of solutions. 1 or 2 or so many. We can count them, finite. Or 0, no solutions. With inequalities, typically what we have solutions over an interval, which means you're going to have sometimes an infinite number of solutions. And so we write those solutions using, and to start with, an algebraic type of notation. These are the four symbols we would use to represent the algebraic notation. And these are ones you're familiar with. The first one is less than or is fewer than. So if x is less than 10, we would say x and then less than 10. Okay, something like that. If we say is more than or is greater than. And so the word is, again, tells us that we're comparing things as like an equation or an inequality of some sort. We talked about that back in 1.3, but we have, let's say x is more than or is greater than a 10. Then it would look something like this. Even if you flip it, let's say we have 10 on the front and the right on the back here, and we have 10 is less than x, which is fine. You can read it backwards. It's sometimes hard for students to do, but x is greater than. See how the alligator's eating the x? Alligator always eats the bigger number. We knew that from grade school. But the x is greater than 10. So you can read it left to right, or you want to get proficient of reading it right to left as well. Is less than or equal to, is at most, and these last two is no more than. These last two we don't use very much, but those are going to be ones that come into play that we have to think about. If it's at most 10, that means it can't be more than 10. So x would have to be less than or equal to 10, because that's what it can be at most is 10. Or it can't be any more than 10. It can be 10, but it can't be any more than 10. It would look something like this. And then what we have is greater than or equal to, or is at least, or is no less than. And again, if we had a statement that's, oh, x is at least 10, that means it can't be less than 10. It can be 10, but it has to be greater than or equal to 10. That's what we're taking a look at there. Okay, let's go ahead and take a look at sort of solving inequalities. When solving inequalities, the goal, not different than the equation, very similar. Remember our goal with equations back in 1.3 and when we talked about absolute value equations in 1.4? We said our goal is to get the variable by itself. We need to isolate the variable. Figure out what the variable is equivalent to. What makes this statement true? With equations, a lot of times, it's just one answer, or maybe two with the absolute values, or maybe none. But with inequalities, notice we're trying to get something larger than 11. Well, tell me a number larger than 11. 12. 11.5, 13, 100, a billion. We can keep going forever. That's why there's an infinite or an interval number of solutions for x, is because we're not looking what equals 11. It could be, but we want to also look for what's greater than. The process of solving this is pretty much exactly the same as solving it as the equation. There's one major exception, and we've got to make sure that we remember this, because this is really what separates inequalities from equations. And what that is if you ever multiply or divide by a negative, you must flip your inequality sign. Okay, and I'll put a star next to that one because that's pretty important. Anytime that you multiply or divide by a negative to both sides of the equation, so multiply or divide both sides by a negative, you must flip the inequality sign. So in other words, instead of greater than, to be less than if that happened. We'll take a look at it on actually the second example. Let's look at the first one though. Treat it just like an equation. Just pretend that's an equation. What do? We try to isolate the x. So we want to get x by itself. So we undo or we move the constants by addition or subtraction. So in this case we add 4. So we're going to go a little quicker because we've done this a few times now. Notice I simply add 4 to both sides. That's your cancellation property. Now what we want to do is we divide. Now we got to be careful because we're dividing. If it's by a negative, we're in trouble. But we're dividing by a positive 5. We're dividing by 5. Notice I didn't say anything about a negative. So nothing happens to an inequality sign. We get x is greater than or equal to 3. So the solutions here are infinitely sized. You can say 3.8 or 4 or 5 or 10 or 20 or a million. All those solutions would satisfy this condition right here. And so this is what we call an algebraic notation. And we'll look at a set builder notation a little bit and then interval notation as well. Taking a look at the second example, what we have going on here is we have the same type of situation, but we need to subtract 3 first. Okay? Then what we're left with is negative 2x is greater than 4. So again, I haven't multiplied or divided by a negative yet, so nothing's flipped. At this point, though, hopefully we notice that we are going to divide by negative 2. There's your clue. We're dividing by a negative. Right there, we need to flip the inequality sign. That's the big change between an inequality and an equation. And if you master that, you're going to be in great shape for this lesson. Graphing the solution. So we know how to sort of find the solutions. We want to get to graphing them. And so we want to take a look at are the open statements. Okay, these two, the less than or greater than, we call those open. And what we do is we omit the endpoint. So in other words, whatever value makes it equal to it, we have to omit it. It's not true. X can't be less than 4 if it equals 4. So we have to figure out where do we omit that value, and then it's everything above that. And so we use an open circle, and when we get to interval notation, we'll use parentheses for this. But we're going to use an open circle to represent something that's omitting. So if x is less than a number, we would go to the number, we would put a circle, and then everything left or less than. Be careful not to always follow the arrows. I know that's something that teachers teach when you're young. It's a great thing. But what happens is when the variable's on the other side, we end up going to the left when it's actually to the right. Because remember, we read it this way. And so x is greater than 3. And so if we wrote it like that, you could see, oh, we actually are going to be shading or graphing to the right instead of to the left. So be very careful of those kind of things. If x is greater than a number, then what we'd have is that number, and we would shade or graph to the right of that value. So here's some examples. X is greater than 2. 2 is our endpoint. We omit 2 because it's not including 2. And x is greater than 2, so it's going to go this way. Down here you can see the reverse. If you followed the arrows, you would probably have been wrong because you would have shaded this way. However, for this problem, if you simply could read x is greater than 2 or 2 is less than x, my x are my solutions is another way of looking at that. So 2 is less than my solutions. 2 is less than the shaded area. 2 is left of the shaded area. There you go. And so we have 2, and our shaded area is to the right. Less than or equal to, same kind of thing, but we're going to include the value now because the or equal to sign. These are called closed statements. And so we're going to be our number, and then we're going to be going to the left, okay, depending on if in this case, my solutions are less than a number, or my number is greater than my solution. So if the number is greater than solutions, here's my number, then that means that my solutions must be left or less than that. And so you can see the two examples down here. X is less than or equal to 2, or 2, is greater than or equal to x. And again, my solutions would be going to the left. So be very careful, especially of the second one right here. A lot of times that gives students some fits if they're not careful. Okay, taking a look at some examples here. And again, I'm going to work fairly quickly through these, and you can rewind if you need to. What we're going to do is we're going to go ahead and get w by itself. That's my goal. So I'm going to add 5. Do it to one side, you got to do it to the other. So no need to flip anything yet. I haven't multiplied by any negatives. Here I'm dividing by a 3. So once again, I'm not dividing by a negative or anything. So I have w is greater than 12. There's my algebraic answer. Now they want us to graph this. And so we go to our endpoint, which is 12. And so I go to 12. It's right here. It's going to be open. How do I know that? My inequality sign is going to tell me it's open. It doesn't include 12.
Now I shade one way because my solutions are an interval. It's an infinite number of solutions. So I go, well, which way do I go? Do I go left? Do I go right? My solutions are greater than 12. And so in this case, I would shade, and you could shade either like this or just draw, somehow making sure I identify that your solutions are to the right of 12. Second one right here, we go ahead. I'm going to go ahead and move my 5. I'm going to move the 6x to the left to keep my variables positive. If you remember, I like that. And so again, I'm just moving things. I'm not multiplying or dividing yet. Now I go ahead and subtract 6x. So once again, I'm not really doing much. And notice, wow, that worked out really nicely. I didn't have to do any multiplication or division. Didn't have to flip your inequality sign. Notice that x is greater than 9. So I go to 9, which is right here in the middle of 8 and 10. It's going to be open. Again, my inequality sign says that. And it's going to be greater than 9. This one right here, you can sort of anticipate what's going to happen here in just a moment. But let's go ahead and subtract 4 first. We'll wait for that. And now here it comes. We divide by -8. Okay, there's your key. Division of a negative. I have to flip my inequality sign. So there's your difference between inequality and equation when it comes to solving in the process. And there's your solutions in interval. Notice my solutions are less than or equal to -1. So I go to -1, it's my endpoint. It's going to be less than or equal to, so it's going to include, it's closed at -1. It's less than means left. And so my solutions are left of -1. Okay? Taking a look, there's quite a bit more here practice. I'm going to go very quickly through these again. First thing I would do on this one, I would distribute. So -15, -3 times 5 is -15. Y plus 12 is greater than or equal to 17. So again, what I've done is I distributed -3. -3 times -4 is positive 12 is how I got that. Now I go ahead and subtract 12. You get -15y equals 5. Oops. Greater than or equal to. Almost messed up there. Here we go. Okay, so what you notice here is I'm going to divide by -15. So again, it catches my attention. I know I've done it a lot more than you, but man, that catches my attention. And so I end up getting something that looks like this, but I've got to flip that inequality sign. That's big. Then I reduce my fraction. I don't like leaving it not reduced, and so I can take a 5 out of both of those. And so we end up getting this fraction. Again, fractions, don't let them bother you. They'll be okay. And so once I go over here, I go to -1/3. It's going to be right around in here. It's going to include it. So as long as you're close, you're in good shape. My solutions are less left than that, and so I would shade this way. Okay, so that's where we would be for a problem like that one. Take a long one over here to the right. This is a very, we'll get to the one to the right here. Let's do this one down here real quick. First off, what I notice is I have a division of 2. I got to undo this division of 2. So I'm going to multiply by 2. That will get rid of that division. Whatever I do to one side, notice why I say you got to do the other side. So the entire side has to be multiplied by 2. Not just the 3, not just the x, but the entire side. And so I'm multiplying by a positive, so there's no trouble there with the flipping of the inequality. Now I can go ahead and get my inequalities, solve for my inequality. So I'm going to move the 3x. I know I'm putting it on the right side, but we can do that. I'm going to subtract the 12 while we're at it. I kept my x positive too, which is nice. It does put my x on the right side, which some students struggle with. So what I get is -2 is less than or equal to x, and that's a fine solution. I need to make sure I write the solution correctly. So I go to -2, and it's going to be closed. So I think that's most of us can see that. But I got to know which way. Again, that's why I don't like you following the arrow, because it looks like you're going to go to the left. But if you read this, -2 is less than my solutions. So -2 should be left of my solution. So my solution should be right of -2, if that logic holds true. If you read it backwards, you can see my solutions are greater than or equal to -2, which is true. Okay. So we go ahead and we head up here to this one. This is very interesting. So we can go ahead and I'm going to subtract x. And oh my, look at what we got. The x's are gone. Okay, and so all of a sudden we have 5 is greater than -4. This is a very special one here. If I said 5 is greater than -4, hopefully your response would be true. Sure it is. 5 is bigger than -4. Okay? Notice I've lost my variables. You're like, well, what kind of statements are true statements? Well, anytime you get an equation or an inequality where you get a true statement where no matter what you plug in for x, it's always going to be true. You give me an x and we plug it in, it's always going to be true. Try it. Try it. Plug something back in and see if it works. I guarantee it will. And so this is called a true statement. Anytime you get true statements, we're looking at all reals. any number. Okay? And so how do you graph something that's every number? Well, you simply graph the whole number line. Just shade it in a little bit darker. There you go. Now the one right below it's very interesting because it's the same type of setup, but if I go ahead and subtract x, notice in this case I have 5 is less than -4. Well, wait a minute. 5's not less than -4. 5's greater than -4. This is called a false statement. Anytime you get false statements in math, which means no matter what you plug in, it doesn't work, then what you're going to get is a no solution. Okay? A no solution. Some students or some teachers will allow you to put the null sign. That's okay. Usually null is used for set notation type of thing, and that's fine since we're dealing with inequalities. That would apply, but no solution would be fine. If you put the null sign, that would be fine as well. What do you graph? Nothing. The whole number line's open because there is no solution. You don't graph anything. Okay, so keep those in mind as we're working through these problems. Okay. Now let's take a look at set builder and interval notation. Now set builder, what we have here is this is what the textbook, this is a really fancy pants way of writing solutions, or algebraic solutions. And so what we have here is we have these braces, okay? We have a line that goes up and down. In math, what that means is such that. Okay, so when you see this means such that. So there's a lot of shorthand in math. So we have the values of x, such that, and then x is going to have some kind of property, and we'll call the property P of some sort. And so for us, again, this is just very basic. In college algebra, you'll get more advanced. But if you take a look here, we're converting an algebraic notation into a set builder notation. And really all you want to do is you want to get used to the braces, the x, such that, and simply all you're going to do is take this. I'm just going to go ahead and grab it and move it over here. Boom, there you're done. There's your set builder notation. So we have x, all the values of x such that x is greater than 5. So there's our condition for x. We're talking about x and such that what? Such that x is greater than 5. Down here, same thing. You can throw it in like this. If you want to go ahead and flip it, you could and put x is greater than -4. Either one would be fine. But that's what we're doing. Anytime you go from an algebraic notation into a set builder, it's really not that challenging as long as you know what you're doing, as long as you see. So mainly it's just exposing you to this. The last one here is a little bit more advanced. We won't have a lot of these, but we want to take a look at it. It says write the first 4 terms of the set described. This is supposed to be in set notation, so I'll need to fix that. But what we have here is we have some, it's not a variable anymore, but we have some kind of formula, some kind of expression, 2x over x plus 1. 2x over x plus 1. And they're telling us the condition for x, such that x is a whole number. Remember back in 1, 2 when we talked about sets of numbers, whole number starts with 0, 1, 2, and then we're talking about the what? The first 4, 3. So those are the first 4 terms in the whole. What they're wanting us to do is describe the numbers if I plugged in 0, if I plugged in 1, if I plugged in 2, and I plugged in 3. What would be those 4 numbers? So when I plug in 0, I get 0 over 1. Well, 0 divided by anything is 0. 0 over 1, that's 0. So that's my first value. If I plug in 1, I get 2 over 2. I get 2 times 1, which is 2, and 1 plus 1, which is 2. 2 over 2 is 1. There's my next value. I then take a 2 and I plug it in. I get 4. And on the bottom, I get 3, because 2 times 2 is 4, and 2 plus 1 is 3. So I get the answer 4/3. And if I plug in 3, you can sort of see the pattern here. We got 6 and 6 over 4. You might want to reduce that to 3/2, and there's your 4 terms. So definitely something that if we didn't take a look at, you may have struggled with. But hopefully now you can handle those type of problems, whatever condition they may give you. Okay? The last thing we want to take a look at in this lesson is this advanced topic called interval notation. And this is something that I'm trying to implement in Algebra 2 a lot more. Definitely with the Common Core, we're going to be utilizing it much more because it is part of the Common Core. But definitely this is something for Trig, Pre-Calc, and for AP. Definitely for AP, this is what we do over the summer a lot, is making sure we got the interval notation down. And really, interval notation is just the same as algebraic, just another way of writing it. And so we have open intervals. We usually use the less than or greater than signs. But with interval notation, we use parentheses, okay, to represent the same thing. And so inequalities that are open, parentheses. Inequalities that are closed, use brackets, okay? So use the brackets. So here is an open statement. So what we have is we from A to B. And what we have, it looks like an ordered pair. I understand it looks like an ordered pair. It's not an ordered pair. What we're doing is we're doing like a starting point, and then we're doing an ending point. And so your solutions are sandwiched in between those. And so if we put something like this statement right here, this compound inequality here in set builder notation, here's your algebraic notation. They all three mean the same thing. If you look at all three of these, let me get rid of that right now, and you can go back if you need to look at it again. All three of those mean the same thing. So if we had a value, let's say my x is sandwiched in between 2 and 5. Something like that. So 3, 4, 2.5, 3.4, 4.1, whatever it is, all of those are sandwiched in between 2 and 5. That can be represented over here from 2 to 5. Not including 2, not including 5. Looks like an ordered pair, it's interval notation. We can do the same thing if it's a closed interval from 2 to 5. This time, though, we need to include 2 to 5. That's where the brackets come in. I include 2, I include 5, and it's an interval notation, so that means that all my solutions are sandwiched in between the 2 and the 5. Then you have some half open, half closed ones, and you can see that you can use a combination of the two. So if you had something like 2 is less than x, which is less than or equal to 5, well, it's open at 2, it's not going to include 2, but it's going to be closed at 5. So my solutions are sandwiched in between 2 and 5, including 5. Same with this one over here. The difference is 2 would be included, 5 would not be. Okay? The ones that get very interesting is when we talk about infinity or negative infinity. Infinity and negative infinity are simply concepts. They're not numbers. Okay, so on a number line, we can't just put our finger on infinity or negative infinity. It just simply means really, really far out to the right on a number line, really, really far out to the left on a number line, sort of a concept here. And so it goes on forever. So if I get a statement like this, x is greater than 3. Well, give me some solutions. 4, 5, 4.5, 7, 10, million, a billion, a trillion. We could keep going. There is no end to it. So how do I write that interval notation? Well, again, where do we start? Our starting point is 3. And when I say start and end, we go back and we said start and end, we're talking the left point to the right point on a number line. This is your start. This is your end. And we go left to right. We're American, we read left to right, same thing here. So I'm going to start at 3. It does not include 3. And then I go to infinity. We will never include infinity or negative infinity. Because this, again, it's not a number, it's just a concept. And so here we take a look and we have x is less than a. Let's put it in this case, less than or equal to 3. So what we have here is if x is less than or equal to 3, graphically we would go to 3 and it would be closed. And my solutions would go to the left. So where's my starting point? It's not going to be 3. That's my end point. I go left to right. My starting point is negative infinity. I never include in negative infinity or infinity. It's just a concept, not a point. But 3 is going to be my end point, and I'm going to include 3. Okay? And so that's called interval notation. Okay, the last thing we'll take a look at is just some basic examples of these. We'll look at a graph and how to do them. So if we look at the first one, this is in set builder notation. If you want to look at the algebraic notation, it would look like this. And this one right here would look like this. So not much different than what you can tell. So this one right here. Notice what we have. Let's graph it first. I think graphing helps us. We start at negative 12. So let's go to negative 12. It's going to be open. Okay? And notice my solutions are greater than negative 12. Or negative 12 is left or less than my solutions. So my solutions have to be this way. So now if I want to do interval notation, I'd say, well, where do I start? What's the most left starting position? Negative 12. How far do I go? Well, infinity. I never stop. Infinity's always going to be open. In this case, negative 12 is also open. There's my interval notation. If we take a look at the second one here, notice my solutions are sandwiched in between negative 3, which is open, and 4, which is closed. And so all my solutions are sandwiched in between those. My x or my solutions. So I go from negative 3 to 4. Not including negative 3, but including 4 as my solution. That's called interval notation. You want to get proficient with that as well, and hopefully with practice we will. Okay. Hope this will help 1-5 solving inequalities. Remember, treat them just like equations, except anytime you multiply or divide by a negative, you've got to flip the inequality sign, and then make sure you're going over the interval notation. That's probably new to a lot of you. Okay, we'll see you next time.